Hey everyone, in this video we're going to be looking at something called a binomial probability. Now you've probably seen this word binomial at another point in math when you were learned algebra. You saw like binomials, trinomials, things like that. Means a little bit different thing in probability and statistics. It's not a two-term expression, if you will. It is something completely different in probability and statistics. But the root of the word bi, of course, means two, like a bicycle is two wheels. So in this case, binomial probability is the probability of something occurring that has exactly two outcomes. So the illustration we use here is a coin flip. That's very often used because when you flip a coin, you either get a heads or a tails. So there's two outcomes, a head or a tail. And we're going to define those as successes or failures. So let's go ahead and look at an example. First of all, something that we could do. So if you've ever seen the show Wheel of Fortune before, they spin this wheel around, they land on something, and then they get to guess a letter. So this wheel here actually has 24 little sections. Right. Now, the best thing to land on, because you earn money by guessing the correct letter, so you obviously want to land on the highest amount of money, and the best one to land on is this section right here, which is 5,000. Okay, and obviously you want to avoid the bankrupts, the lose the turns, all that. But the best one is 5,000. So what if we ask the question, what's the probability of a contestant spinning 5,000 on 3 consecutive spins? Well, this we could actually do with what we know right now, because essentially we need a 5,000 and then a 5,000 and then a 5,000. So this is an and probability. So this would be like probability of 5,000 and 5,000, right? And 5,000. Oops. Okay, so the way that you would actually do that would just be, well, the probability of landing on 5,000, which is 1 out of 24. And remember, and probabilities you multiply, so times 1 out of 24 times 1 out of 24. So that's going to be a really low chance, right? Now, if I were to change this up a little bit and ask a question like this, what's the probability of getting 3 $5,000 spins if we were to spin this wheel 100 times? So adding a little bit of a different dynamic to this, we're going to spin it 100 times instead of just the 3 times and see how that would change our odds. So to answer this next question, we actually need a little bit more in-depth formula, a little bit different way of solving this. So that's what we're going to learn today. We're going to be talking about binomial experiments, which what we just outlined are. And these are probabilities in which there are two outcomes. So if we were to flip a coin, heads or tails, and the example that we just looked at with the Wheel of Fortune wheel, the two outcomes in this one are either 5,000 or not 5,000. So we're only considering whether we're getting the 5,000 or not the 5,000. All the other things aren't really considered in our experiment. It's just, did we do it or did we not do it? So that's a binomial experiment. Did we do it or did we not? These were first studied extensively by a Swiss mathematician. His name was Jacob Bernoulli. He actually has his own distribution as well, and he studied this in the late 1600s. So the conditions of a binomial experiment, which if we're going to do binomial probabilities, we've got to have a binomial experiment. First thing that always must be true is there are a fixed number of trials. Meaning before we do anything, we're going to say, well, we're going to spin this wheel 100 times, or we're going to flip the coin 50 times. So there's a fixed number of trials. It doesn't change as we go along in our experiment. The next thing is the number of n trials is independent. Okay. Independent, meaning the spin or the coin flip or whatever, the previous one does not affect the next one. So we learned about this in the last chapter, identifying if things are independent or dependent. Right, dependent things change based on the previous draw or coin flip or whatever. So like if you had a deck of cards and you did not put it back in, that would be dependent. If you put the card back in and reshuffled it, that would be independent. And also these trials are repeated under identical conditions. So we're doing it exactly the same way, each of the trials. And each trial has only two outcomes. This is kind of the biggest thing that defines binomial experiments, is there's always only two outcomes. Either you have a success or you have a failure. So either you spin the 5,000 or you don't spin the 5,000. Either you get a heads or you don't get a heads. Either you pass the test or you don't pass the test. So success or failure. And last thing here is that the probability of the success is the same in each trial. So if you got a 50% chance in this one, the next one you also have a 50% chance. Or if it's a 1 out of 24, then the next one is a 1 out of 24. And the next one is 1 out of 24. So the probability of success is succeeding is consistent throughout all of the trials. And often the goal here is, we'll define this with a formula in a minute, but is to find the probability of the number of successes, which we'll call R successes out of N trials. So the probability of 3 spins out of 100, right? 3 5,000s out of 100 trials. So if we were to go back and look at just that second part of the question, do these all apply? So the probability of getting 3 5,000 spins if a contestant were spent 100 times, right? Fixed number of trials. Yep, because there's 100 trials. Next thing, each one is independent under identical conditions. So to satisfy that one, we would have to make sure that you're spinning it exactly the same way, starting at exactly the same spot each time to ensure that's the case. Next one, each trial has two outcomes, success or failure. Yeah, that would be true. It's either 5,000 or not 5,000. And the probability of the success is same in each trial. Yep, that would be true because when you spin the wheel, you don't create another 5,000 or anything. The wheel stays the same throughout the whole time. So that would be true as well. So that one we could qualify as a binomial experiment. Yes. So in order to solve for the odds of one of these things happening, we do need a formula. This is what the formula looks like. Looks a little bit intimidating at first. But you've seen all of these symbols for the most part here. That's the probability of R, and remember R represents the number of successes, equals n factorial. Remember that's what the exclamation mark is. It's a factorial over R factorial times n minus R factorial times P to the R times Q to the n minus R. So this part is actually, this is the new part. This first part is actually a formula we did in the last section. And that is a combination. This is the formula for a combination. So that n choose R. So when we actually evaluate this, what you can do is just use on your calculator the NCR button for that first part. And that's probably how I'll do it. So what all of these variables represent, n represents the number of trials. R represents the number of successes. P represents the probability of success. Q represents the probability of failure. And all right. So there's our formula. Definitely take a second to write that down. You will need that one for all of these problems. All right, so let's go ahead and do a couple examples here. All right. So this problem I actually found when I was looking for examples on the internet, which is kind of funny because I didn't even change the names or anything. It says Mr. and Mrs. Davis, which actually would be my wife and I, are planning to have 3 children. And the funny thing is we actually are, we have 2 kids and we are going to have a third one. So that's kind of crazy. So it says the probability of each child being a boy is 50%. All right, you got a 50-50 chance. So what is the probability that they will have exactly 2 girls? All right, so you're going to have 3 kids. We actually have 2 already. We're going to have a third one. So what's the probability that we're going to have exactly 2 girls? And just show you there's my first one. His name is Blaze. He's a boy, obviously. And then this is Arden, a little girl. So that's what I have now. Blaze is at his dead tree fort there, and Arden likes to dress up like a princess a lot. So there they are. So basically, I'm kind of on track to have 2 girls, right? That's still a possibility. And in fact, we are going to have another girl. So what if from the outset, my wife and I said, We want to have exactly 2 girls. What are the chances of that happening? Okay, so it turns out we could figure that out. Let's start by identifying the variables. So we need an N, an R, a P, and a Q, essentially. So let's first start with N. So number of trials. Well, this one maybe is a little hard to identify, but it's total number of children we're going to have. We're going to have 3 children, so N is 3. We might have more than that, I don't know. But for now, we're going to have 3, and so that's their total number of trials. Next thing we need is an R. So R represents the number of successes. So in this case, well, what is considered a success? A success here is having a girl. That's how a success is defined in this particular problem. Having a girl is a success, right? Because we're trying to have 2 of them in this scenario, right? So R would be exactly 2. It's exactly 2 successes. P represents the probability of success. So the probability of having a girl, which is 50%. So I'm going to write that as 0.5. I do want those as decimals. And then Q represents the probability of a failure. And the failure in this case would be having a boy or not having a girl, right? So it'd be 0.5. All right, so that's all we need. Just identify those 4 variables, and then we're going to plug them into our formula. And I'm going to use the combination formula. So it's going to be, so the probability of 2 girls equals combination N choose R, so 3 comma 2. And then it's P to the R, so that's 0.5. I'm going to put it in parentheses to the R, which is 2. And then probability of failure Q, 0.5, to the N minus R, so 3 minus 2. So that is our setup. We just plug everything exactly into that formula. C is N comma R equals times P to the R Q to the N minus R. So I just substitute all those in. Next thing I'm going to do is just pull out my calculator. And remember, to get the combination formula, how you get there is you do math, hit the math button on your calculator and go over to PRB. And then it's the NCR. But the other thing to remember is you got to type the 3 in first. So you do 3 NCR and then 2. So you type the 3 first and then you do the math PRB. So we're going to do that. 3 math over to PRB NCR 2. Just hit enter, and that's actually 3. And I'm just going to go ahead and times, and then just type it in exactly, really how I have it written there, 0.5, the second power, and then another parentheses. I know 3 minus 2 is 1, so I'll just do 0.5 to the 1, first power. And that equals 0.375. And let's go ahead and make that a percentage. So that is a 37.5% chance. So the probability if you were to have 3 kids of having 2 girls would be 37.5% chance. So our odds ended up being, again, that we're having a boy and 2 girls. So there's a 37.5% chance of that happening. You could take this the opposite way, and you could say, what is the chances of having exactly 2 boys? And that would be also actually 37.5% because the odds are the same. You could calculate, well, what's the chances of having 3 girls or 3 boys? In the same way, you could do that. So number of different ways you could do that. For the next example, for football, a field goal kicker is accurate 75% of the time when he's within 35 yards. So what's the probability that he's going to make exactly 7 of his next kicks from within 35 yards? So we need to identify our 4 variables, our N, which is the total number of trials. So he's going to make 10 kicks. So that's the total. And then next would be R. So let's think about what R is. It's a success. So what is a success? A success equals making a kick, right? So R, when we're trying to get exactly 7, so R would be 7. And also N should always be bigger than R. You should always have at least as many trials as you are successes. I suppose it could be the same, but N should always be at least as big. Next up, we need P, the probability of success. So it says he's accurate 75% of the time. So that would be a success. He's successful 75 or 0.75% of the time. Now to find Q, you might not know this. I guess maybe I didn't say this before, but Q is always 1 minus P, right? So if we're successful 75% of the time, then Q is going to be 1 minus 0.75, so it's 0.25. It's always 1 minus P. You might want to make that Q equals 1 minus P. Write that down. All right, so now we've got our 4 variables. We can plug them in. So the probability of, let's say, 7 makes, and do write this out so you're saying what you're actually doing. Probability of 7 makes would be C10 comma 7. And then we got the probability of success is 0.75 to the R, which is 7, times 0.25 to the N minus R, so 10 minus 7. So that's how we'll plug it in. We'll do 10 math over to PRB, NCR 7. It's 120, and I'm just going to hit times, and then parentheses 0.75 to the 7th, and then times parentheses 0.25 to the 3rd power. And that is 0.250, so 25% chance. So 25% chance he'll make exactly 7 of his next kicks. Now, if the question were changed a little bit, if it had said at least 7, if it was at least 7, then we would need to do the probability of 7 plus the probability of 8 plus the probability of 9 plus the probability of 10. So we'd actually have to do 4 separate calculations and add those up. But this is saying exactly 7. And same with the previous question. I specifically said exactly 2 girls, because if it was at least 2 girls, then I would need to do probability of 2 girls plus the probability of 3 girls. All right. Last example, we'll kind of practice this. So on your Prob and Stats final exam, there's 3 multiple choice questions which you had no idea how to solve. Each of these questions has 4 possible answers, right? A, B, C, or D. And you randomly selected answers to these questions. What is the probability of answering at least 2 questions correctly? All right, so let's see if we can identify our variables. Oops. N represents the number of trials. So the number of trials in this case represents the number of questions, right? So there's 3 questions left. That's our number of trials. R represents the number of success. Now on this one, we want to know the probability of getting at least 2 correct. So a success would be actually getting 2 correct, or it could be getting 3 correct, right? Because that would still be successful. It'd be even better if we got all 3 correct. All right, the probability of success. This is maybe a little bit more challenging. On each of these questions, there's 4 answers, right? A, B, C, or D. So the probability of you getting it right is 1 out of 4, or 25%. Either way, you can write it. It's fine. And so then the probability of failure, you can probably figure that out with the complement of that, which would be 3 out of 4, which is 0.75. So I've got all we need to go ahead and set this up, except since this was at least 2, we're going to be adding 2 of them together. So the probability of 2 or 3 correct is going to be a combination 3 choose 2, 3 comma 2, 0.25 to the R, which in this case, the first R will be 2, times 0.75 to the N minus R, so 3 minus 2. And then we're going to compute that, and then we have to add the probability of getting 3. So that's going to be C with 3, choose 3, because we're getting all 3 correct. So in this case, our R was 2, and this is when R is 3. The N remains the same in both. All of the other things do. And then we've got 0.25 to the third power times 0.75 to the 3 minus 3. So do those two computations. First one, 3 math over to PRB and CR2. And that is 3. So 3 times 0.25 to the second power times 0.75 to the first power. And that is 0.140 plus the next one is just going to be 3 math NCR3, which is just 1, times 0.25 to the third power times 0.75 to the 0 power. Anything raised to the 0 power is just going to be 1 as a whole, so I'll put it. But when we do that, we get 0.015 approximately. So add those together, and we get about 0.155. Or we could say about 15.5% chance. So actually not great. Not great odds of getting 2 or 3 of those correct. All right, so that does it for these questions. If you are struggling with this, make sure you do reach out. The most important thing in answering these is getting the N and the R, really all 4 of these variables, identifying those first. So think about what is defined as a success in the problem, how many trials are there, how many successes are we trying to measure, what is the probability of a success, and what is the probability of a failure. If you identify these 4 things correctly, then it is very easy plugging it into the formula. So, all right, good luck with those.